senses between the sensories and those neurons and the limbic system, which basically controls things like various autonomic responses, such as fight or flight. I mean, the first thing that you want to do when you see something interesting in the field of view is immediately assess whether or not it's going to eat you or it's something that you can eat. It's a very, binary decision. And the brain can't waste a lot of time bringing this stuff to consciousness and then having you logically parse all the possibilities for that shadow that you see in the forest over there. You have to act immediately. And so it turns out that the brain is very comfortable in tagging sensory information with any number of things that it finds useful in helping you survive. Well, it turns out tagging things with color connects directly with the way light reflects off of various interesting things in the environment. For instance, light reflecting off of green leaves or leaves on a plant comes out as a greenish sort of a tinge. So when you look out in your visual field, it would be nice to be able to tag information that you see in your visual field with the color red or green, in this case green, because that would tell you the direction to go to eat plants if you're a herbivore, or to find plant eaters if you're a carnivore. So green comes out to be a very useful color. That's the product of essentially the visual spectrum from the sun interacting with the chlorophyll in plants and producing specific wavelengths of light, which the brain then codes as the color green, because it's got to code it with something to separate it from all the other colors. And then you have things like blue. Blue is an interesting color because in many situations, water has a color of blue from the reflected light from the sky. So it would be useful to have some kind of a tag that looks at your visual field presented by the retina and says, oh, there's blue over there. And if you're thirsty, that's something that you ought to be looking at in order to get water. So, you can make the argument that the reason that we have, these kinds of primary color sensitivities and their combinations has a lot to do with the way that light interacts with things in our environment and then throws specific wavelengths of light at us for our brains to process and to do that as efficiently as possible for survival. Well, the way that this all works, I'm going to give you some examples. The beginning example is just the basic idea of how filters work. What we have is sunlight coming into the filter. Let's say that there is as much sunlight coming in the red part of the spectrum as in the mid-yellow or in the shorter wavelength blue part. Let's say the 100% is split 33%, into each of these. We're going to put a filter in front of that light, which is only going to pass 55% of the red light, 30% of the yellow light, or 15% of the blue light. And so the question is, what are you going to get as a result of this filtration? That's a fairly straightforward calculation where basically you just multiply things. In this case, 30% is red, so that's 0.3 times 0.55, which is 55% for the red filter. And that gets you 0.165, which is 16.5%. The yellow, you calculate it the same way, and you get only 9%. And for the blue, calculate it the same way, and you get 4.5% using the numbers as shown. Now, what we have here is a filter, okay, which if you add up the percentages in the filter, the 55, the 30, and the 15, you get 100%. So this filter is going to pass 100% of the light that falls on it, guaranteed. That light is going to come out for the particular combination that I've shown here. The alert members of the audience might realize that if you add 30% and 30% and 30%, you get 90%. You don't get 100% sunlight. So, okay, I made a mistake. That 100% should be 90%, but that isn't going to affect anything further on down the line. So we've got, for the red filter, it passes 16.5% of the light. The yellow passes 9%, and the blue passes 4.5%. If we normalize those percentages total to 100%, that works out to the numbers that you see in that second rectangle, where 55% of the applied light comes out through red, 30% comes out through yellow, and 15% comes out through the blue filter. And so that adds up to 100%, which is what we want for the total light that we're looking at. So if you were to look at these percentages, clearly there's not much blue light that's coming through this system. There's a little bit more yellow light, but there's a fair amount of red light. So what you're going to perceive if you put that filter against our model sun is you're going to see kind of light with a reddish tinge to it. And that's basically all there is to filters. Filters basically knock down the amount of incident light by certain percentages. The specific way in which a filter works is determined by the kind of materials that are in the filter and what their various wavelength responses are. All filters can be tailored to pass certain types of light and block other kinds of light at different wavelengths. And so that's essentially the magic of it all. If you want a yellow filter, then what you do is you create a filter that passes almost no red light and no blue light. So essentially everything that comes through it that's yellow gets passed through as yellow. And that's what you see there. And correspondingly, if you have a filter material like an organic compound that doesn't pass any of the blue and doesn't pass any of the yellow, but passes most of the red, you're going to see something that looks reddish. So that's basically the mystery of filters and how you can think about them sort of mathematically. As an intermediate kind of a problem, we can think a little bit more carefully about what sunlight looks like. That figure shows you a rendition of the electromagnetic spectrum over this very long wavelength band. And the colorized portion of that is the visible spectrum. You see the sort of bluish purplish part is at maybe about 450 nanometers on this scale. And by the time you get out to about 650 nanometers in the far red, you've lost really any sense of color. This is the visible spectrum perceived by the eye. These aren't colored wavelengths coming from the sun or anything else. This is essentially a measure of what the human eye does to incident electromagnetic radiation in the visible spectrum and the way that it codes different combinations of the primary colors, which are basically red, blue, and yellow, or red, blue, and green. Combinations of these things in filters can give you, all the other colors. But these wavelengths are unique to each of those colors and the way that certain cells in the human eye respond to them. We have cone cells in the retina, 3 cone cells for every resolution element. And these cone cells are sensitive. One might be sensitive to blue, one might be sensitive to red, one might be sensitive to yellow. And so the retina will report out for that resolution element a certain amount of neural activity for the cones that do the red, the blue, and the yellow. And the combination of those 3 is done in the brain to give you whatever that combination color is that the brain likes to tag those wavelengths with. So anyway, as I said, color is a feature of the brain. If you look up terms like qualia, Qualia, you will find all sorts of other things that the human brain likes to do that are imponderables. It's of interest that certain aspects of our perception of time are also a qualia. but that's a whole other talk. Anyway, light doesn't come in colors, comes in wavelengths. Light at different wavelengths will be scattered by dust in different ways. And this gives the atmosphere and volcanic ash plumes, for instance, their characteristic color. Atmosphere dust particles tend to be very, very small, less than a few hundredths of a micron in size, whereas volcanic ash dust tends to be micron-sized stuff, hundreds to thousands of times larger than the dust grains in the atmosphere normally. So the colors that we see depend specifically on the kinds of materials that we're looking at. And so what I'm going to do is give you a little bit of an example of how that works. Suppose we have the atmosphere has typical dust particles, a tenth of a micron or less in size, and the dust particles from volcanic ash is about 1 to 1.5 microns in size. So I created this little table here that gives basically how much of the light at these different wavelengths is scattered. Now, there are two things that you can do to light. You can transmit it through something, or you can scatter it. Scattering means that you're taking that light out of the direction of the light that you're seeing. This is often wavelength dependent. You can think of it as taking light that comes into your eye and subtracting specific wavelengths from that light. And that process is called scattering when you do it. Transmission is simply the direct passage of the light through the medium and into your eye. It turns out that scattering plus transmission adds up to 100%. I mean, you've either got to account for it as light being removed from the beam or transmitted by the beam. And so adding the two together gives you 100%, which means that the amount of transmitted light that you see is going to be 1 minus the amount of scattered light, all right, where 1.0 is the total, all right. So here's how it works. For dust particles in the atmosphere, they tend to scatter about 60% of the blue light at this wavelength, about 40% of the light at 550 nanometers in the middle part of the visible spectrum, and about 10% of the light at longer wavelengths. Scattering is bad because that means that if you look at the complement of these numbers, 100% minus 60% is 40%. So at 450 nanometers, the atmosphere is transmitting 40% of the blue light. But if you go over to the long 650 nanometer red light, 100% minus 10% is 90%. So that means this atmosphere is transmitting over 90% of the light that falls at that wavelength. And so that means that whatever you're looking at that has these filter properties given by these percentages is going to take ordinary sunlight and convert it into something that's very red, because that's where the least amount of scattering by the dust particles is coming from. Now, if you look at volcanic dust, it's crazily just the opposite of that. The amount of scattered light from volcanic dust at short wavelengths is only 10%. But when you get up to the red part of the spectrum, it's over 60%. That means that for volcanic dust, it's going to look, if you take 100% minus 10%, it's 90%. 90% of the light that you see transmitted at 450 nanometers is going to be blue. So this basically says that if you look at anything through the ordinary atmosphere with its ordinary particles, it's going to appear redder and redder the closer you get to the horizon. But volcanic dust, it's going to get bluer and bluer as you look through more and more of the volcanic dust. It's just the opposite. This example basically steps you through a little bit of how to work out these numbers. the caveat here, and what makes this a little bit more complicated, is that sunlight itself, it doesn't have the same intensity at all wavelengths. I mean, you see from this figure here, a lot of the emission comes out in blue, a little bit less in sort of green, and a little bit less than that in the red. So it's a declining sort of intensity in sunlight as you go to longer wavelengths. And so we account for this by that sunlight row at the bottom of this table, where we're saying, okay, let's call what comes out in the blue as 100% intensity. What comes out in the green or red, or rather yellow, is 85%. And what comes out in the red is about 75%. So that's what the light coming in to the atmosphere looks like. And now we're going to modify that even further by having that light go through these various types of materials, the ordinary atmosphere and the volcanic dust. And so we do that calculation for the sunset with ordinary atmospheric dust, and we do it wavelength by wavelength, blue, yellow, and red. And so we had 100% of the sunlight in the blue from that row number 4. And then the atmosphere is scattering 60% of that. And we see that from row number 1 at the top of the table. That's how much it's scattering. And so we get 60% of the light in the blue part of the spectrum is scattered. And we follow that through, going step by step. And now we ask, in the second column, how much of the light is actually transmitted? How much of this light is what we actually see? And you do that calculation. Well, we know what the scattered amount is. And I said that scattering plus transmission has to equal 100%, because you have to account for every photon of light from either one mechanism or the other. And so we see 100% minus 60 gives us 40% of the available sunlight in the blue part of the spectrum is transmitted. But then we get out here to the red part of the spectrum. It's only scattering, less than 8% of the light at that wavelength. So 92% of the red light coming from the sun is actually transmitted. So that means the bottom line here is that for ordinary dust, if you have enough of it, your sunsets or the coloration of the sun at low elevation angles on the horizon is going to look decidedly red. Okay. Now for volcanic dust, we do exactly the same calculation, except now we're using the volcanic dust scatters 16% of its light in the blue, 50% in the green, and 70% in the red. Work those numbers through, and here we get the blue transmitted light is 84% compared to only 48% for the red part. So that means that if you're looking through volcanic dust in the atmosphere at something really bright like the sun, at whatever angle, it's going to come out decidedly blue. Now it's curious, you've probably heard the expression blue moon. It's an odd kind of an expression, because generally it's supposed to mean 2 full moons in the same calendar month. But it's also possible to photograph the moon under the right light conditions, like if there's volcanic ash present or whatever. And if you look at the moon, sort of low elevation angles to the horizon, it will look decidedly blue. Now, I scoured Google images with every keyword I could find, and I found a couple of examples of distinctly blue colored full moons. But I couldn't make up my mind whether these were actually photos or they were somehow retouched just to make the moon look really, really blue, because the articles always had to do with the chronological blue moon, 2 full moons in a month story. So anyway, if any of you know of any genuine photos of a real blue full moon seen in the sky, first of all, you need to run for cover, because that means you're dangerously close to a volcanic plume. But if you do hear or see something like that, I'd be keen to find out if you can document that it's an actual photo taken with a real camera and not something that was photoshopped. Okay, advanced. Believe it or not, that previous one was a sort of middle of the road sort of a problem because basically it's working with percentages and fractions and stuff like that, and sort of intermediate. What we're going to do is take a step up. The way that electromagnetic radiation scatters off of matter, particularly spherical dust grains, is called Rayleigh's law. And basically, there are physical formula for everything at this point. There is a law which says that the amount of scattering that a particular dust grain does is 1 over the 4th power of the wavelength. All right, well, that's a kind of an innocuous equation. This I is the resulting intensity. I0 is the amount of light falling on the grain. A is a constant. Don't worry about it. Don't worry about what that constant is. But the important thing is that it's a single variable function. So it's basically 1 over the wavelength to the 4th power. That's basically taking on your calculator, the x to the 2 key and hitting it twice to get x to the 4. It sort of works like this. What we're going to do is we're going to use Rayleigh's law to explain why sunsets are red and why the sky is blue. Again, it's the same problem we've been sort of, beating ourselves over in the past examples, mainly because I always find it interesting to explain to the public why it is that the sky is blue and sunsets are red. It seems to be something, like why are there black holes, or why can't I balance my tax statement? Well, no, maybe not. That's probably a bad example, but it's sort of a prevailing, interesting, sort of question that people have, especially children. So what we're going to do is step through how we do this calculation. Well, we have 2 wavelengths we're dealing with. We're dealing with a red wavelength at 650 nanometers, and we're dealing with a blue wavelength of light at 450 nanometers. So this is a plug and play problem. You basically plug those wavelengths into the formula, take their 4th power, and you get these very fine-looking scientific notation numbers. You get 2 of them, 1 for each wavelength. And now you can do something really clever. You can take the ratio of these 2 and figure out how much more blue light is scattered than red light. Well, it turns out that if you take the ratio, you get a number that's 4.3, which means that roughly 4 times more of the blue light is scattered than the red light for this particular pair of wavelengths under these conditions. So this is why we have that situation with, the more dust there is in the atmosphere, the more things are going to tend to be red in color for the typical atmospheric dust grains that we have hanging around. Now, what we could do is something very clever. And I'm very proud of this because I'm working on these kinds of problems. I want to see how you can wrangle ChatGPT into a physics classroom without basically usurping the role of the teacher or the student in the learning process. Well, it turns out you can do this just fine because what you do is you treat ChatGPT like an intelligent calculator. Some of us went through the early 70s, the transition between slide rules and electronic calculators. And there was always this controversy, well, should we let students bring calculators into their final exams? And of course, the resistance was overtaken by just their practicality that, well, of course. And so within about 5 years of Texas Instruments and HP developing these inexpensive scientific calculators, basically students use them all the time. I had an HP 13C scientific calculator in my chest pocket. I didn't have a pencil protector like the older generation rocket science did. I had an HP slimline calculator, and I carried that thing with me all over the place in graduate school. Well, anyway, For ChatGPT, it works perfectly well if you present it with a specifically designed question. You will get the same answer over and over again if you use a specific formulation for the question you're posing. Here is the question that I posed to ChatGPT. Using Rayleigh's law, calculate how much more blue light at this wavelength is scattered than red light, and show the calculation. Well, all the stuff that you see below that query sentence, it was done by ChatGPT. All right, and this is ChatGPT talking at you. All right, the answer that it got is 4.35. I didn't tell it to give the answer to one significant figure, so 4.3 is my answer, and 4.35 is ChatGPT's answer. But I didn't have to tell it what Rayleigh's law was. I didn't have to tell it how to use scientific notation. I didn't have to tell it what a nanometer was. It figured that out by being a dumb, stupid calculator, because it doesn't have a brain to know what these things are. All it does is quote other people's definitions, right? And so it got this answer. You can reproduce this by changing the wavelengths and generate a whole range of filter properties just by putting in the same question and changing the wavelengths in the two parenthetical areas. Have students create filters that are really complicated, and it'll basically tell you what the amount of scattering is in pairs, between pairs of these things. And I can imagine all kinds of interesting, fun games. Well, the concept of mathematics and the concept of the game seems kind of contradictory, but I can assure you a lot of these things are kind of fun. I absolutely was bowled over when I plugged this sentence. I wasn't even sure that it was the right sentence to phrase for ChatGPT. And it gave me this line by line way of how it worked it out that was sort of bang on. My only grievance with it was that it didn't have to do the conversion between nanometers and meters. It could have left the wavelengths in nanometers, and the answer still would have been 4.35. The reason is that whether it's a nanometer or a meter, that's all taken up in that constant A that I talked about, which basically has a lot of interesting numbers in it that sets the scale for the resulting intensity. Well, anyway, so there you go. Next time, okay, the sun shows it's going to be performance art. I am not going to do disco for you because that will send most of you to the psychologist bench in a moment or two. But anyway, I'm going to look at a couple of things. The thing that I really enjoy is music and song. So we're going to do an interesting thing. It was popular long time ago to see if the sunspot cycle was correlated with all kinds of crazy things. Because who knew? Who knew what was controlling the ups and downs of the stock market, or the hemlines of women's skirts, or the length of men's ties, or the ability for farming acreage to produce good crops. So they basically, for the 1800s and the early 1900s, they threw everything they could think of at the 11-year sunspot cycle to see if it correlated with anything. But we're going to look at basically the number of songs that are released every year since 1950. I created this archive, and it's an Excel spreadsheet, which I'll share for you as a data set in the next lecture, and you can sort of try your hand, maybe add more songs. I only found about, I guess it was about 130 songs. Sadly, many of them I knew the titles and the performers, and I could probably sing half of them. So that kind of shows where I'm at. But anyway, try something also along the area of arts correlated with the sunspot cycle. And think about how you would set that problem up. Okay, well, that I believe is it. And let's see, I'm going to stop share. Oh, I can do that down here.
Yeah.
And here I am.
And I'm back too because there's some questions that came through in the Q&A.
Oh,
Thank you
okay.
all. One that Tom Thomas asked, why is our closest star categorized as a yellow dwarf star on the HR diagram?
Well, it's a dwarf star because of its mass, and it's a yellow star. Once again, this idea that the sun is a yellow star goes back before the time that astronomers astrophysically understood stars very well. It was determined on the basis of what stars look like. And of course, if you look out in the sky at stars like Betelgeuse and Antares and Aldebaran, you see that they're blood red. Okay, so people thought, hey, color is an interesting thing to use. So let's see if we can find other colors. Well, they found some stars that look greenish and others that look yellowish and whatever. So our sun got labeled as a yellow G-type G25 main sequence star. Dwarf. Well, it's it's not a 1-4. It's a 5. But anyway, yeah, it's just a historical convention that sort of has persisted. There's no particular reason to change it. I mean, everybody now knows the sun is a yellow star, but if you scratch your head and really think about it, it doesn't have a color at all. That's all atmospheric magic. That's done by the guy behind the curtain, as it were.
Okay. And Michael, are you still on? Would you like to ask your question? Because I thought that was very interesting. Michael,
Probably the longest answer for the shortest question that I think I've encountered so far.
Okay. Can you see the answered Q? If you click on Q&A, can you see?
Oh, I actually haven't experimented with that yet. Oh, okay.
So click on Q&A, and then you'll see Tom Thomas's first question, and then Michael asked a question from Montana. You see that when I draw two circles, one inside the other, I see the space thicker at the top rather than the bottom.
Well, I'm seeing two open questions, 7 answered, and nothing dismissed. Is that where I'm supposed to be looking?
Look at the answered one. Click on that tab.
Okay.
And then you'll see their questions, and I tried to answer.
Oh, there you go. You learn something every day. Okay. All right. Well, we did the main sequence, the color type of the sun. I don't see any other. Oh, Tom Thomas. Oh, okay.
And then you see Michael's question, Michael Waltz from Montana.
Okay. Okay, here we go. When I draw two circles, one inside the other, I see the space thicker at the top rather than the bottom. It was mentioned that the thicker atmosphere was at the bottom. Okay, here we have a couple of things going on at the same time. Our visual system, the human retina combined with the visual cortex, likes to deconstruct images into lines at different angles and with different widths. And there are any number of optical illusions out there that basically fool the brain into thinking one thing is going on when it's actually something else. For instance, the Necker cube, is just one piece of continuous wire, but if you look at it rotating, sometimes it forms a cube and other times just a kind of a snaky looking, wire. I think that's the issue of, drawing two circles, one inside the other. The atmosphere being thicker at the bottom, if you're looking at the horizon, is absolutely correct. Okay. Oh, wait a minute. I know what you're talking about. I'm sorry. You're saying that you've got two circles. The inner circle is the surface of the Earth, and the outer circle is the top of the atmosphere. Well, if you draw a tangent line at any point from the surface of that inner circle and have it go straight out to the outer circle, you can see that you can vary the length of that segment between the inner circle and the outer circle just by tilting that tangent line more of an inclined angle. You get your shortest distance if you tilt that line so it's completely vertical at that point. This is the effect that you have less atmosphere when you look straight up at the zenith between the surface of the Earth and the top of the atmosphere than you do if you look towards the horizon. In that direction, you're looking through the maximal amount of atmosphere along that very long tangent line. And that's what it is. The more junk you have in the way between you and the sun, the more scattering will happen, and the redder the light will appear if it's ordinary dust particles in the atmosphere. The other way is that if you have volcanic dust in the atmosphere, it'll appear more intensely blue at the horizon and less intensely blue as you move higher and higher above the horizon. So the deal is you got to get the full moon as it's rising above the horizon to get the full blue moon effect, if that's what you're going for photographically.
Mm-hmm. Interesting. Does that help, Michael? I thought I had enabled everyone. Maybe I didn't enable you to talk. Is that the problem? Yes. Okay. You should be able to talk now if you want to do a follow-up question.
Okay, hello.
Hi, there you go. Thanks for your
Yeah,
patience.
so you're not looking at parallel lines, you're looking straight up from your position on Earth.
I'm sorry, could you repeat the beginning of that again?
Okay. So if I have two circles.
Yeah.
And I look at the equator position. So from the equator straight out, that's a shorter distance than from the North Pole straight out.
That's right.
Okay.
But at the equator position, you're looking towards the zenith. If you're standing at the equator, you're basically laying down on your back in that diagram. So you're looking actually at the zenith when you're looking through that shortest direction. So you have to rotate your viewing horizon along with moving your where you're standing.
Perception. Thank you.
The horizon is always going to be the tangent plane at the location that you're standing. So if that's at the equator, then the tangent plane viewing is going to give you the highest extinction and the greatest path. So that's, yeah.
Does that help, Michael?
Yes, thank you.
Okay. And Tom, are you good with your HR explanation so that you can explain it to your kids, to your students?
Yes. Well, yeah, it's much better. I'll be more accurate from here forward. Thank you. Much appreciated.
Are you doing the HR diagram with your 5th and 6th graders or upper level kids?
We no 5th and 6th grade. I do bring it to their attention, and so we did the with Navajo astronomy with the certain asterisms. I challenged them to identify where on the HR diagram at least one of the stars within their asterism is that star, and they would identify it. That was fun.
Yeah,
but that way I wanted them to think about it.
Yeah, I'm not really suggesting that you really bear down on the fact that the sun is a white star and confuse the issue, because historically we've called it a yellow star for centuries. And quite frankly, as an astronomer, I'm perfectly fine with that. It's only when you get into actual physics courses that you got to get it right and realize that it's actually white light. But yeah.
Yeah, and I've learned it as white light, so that's easier for me to make the connection there.
Yeah.
But yeah, much appreciated. Your explanations are very helpful.
Oh, thank you. I think they're mostly correct.
Pardis, I see you're unmuted. Did you have a question? Are you Karen? Okay. And Anonymous, you asked if you could get the slides, and I posted the link to the Google folder where we put the slides and the recording at the day after. So I'll put them up tonight, but I always like to check it the day after so I don't say they're ready yet. And then I'll send up an email to everybody tomorrow. Any other questions? I looked around a little bit when you were talking, Stan. I used to have my little sailboat was called the Blue Moon. So I actually love blue moons. And so I thought, well, I bet I can find one. And I looked around a little bit and couldn't find one. But it's tough to get the right query too, because so maybe the clue would be when you look at it. So what you said, if you look at it on the horizon, after a volcanic eruption,
Yeah.
then there might be a picture. I can't imagine there isn't one, you know?
I can't either, but who knows? Yeah, for one of the slides, I actually had a picture of the sun being blood red on the horizon, and next to that I had a dazzlingly blue moon, full moon. And about an hour before this presentation, I sort of went back and looked at it, and I said, that moon picture, there's something about it that just doesn't look right. Okay. And so I went back and I looked at the original article, and it was, yeah, okay. I couldn't guarantee that they hadn't retouched it. So I dropped it out, and then I had to drop the whole slide out. It was actually a kind of neat slide. But I want to give you something that's technically accurate and citable in a research paper. I don't want to give you something that's artificially generated. But
Yeah, your kids might catch up. Anybody else have a question or a comment?
I'm actually contracted to write 2 books before Christmas. One is on the essential nature of time, and the other one is the essential nature of black holes. So I'm going to be very busy this summer, having the time of my life, explaining both of these in 25,000 words or less, with lots of illustrations that I can get that are copyright free.
Sounds great.
Wow.
Yeah.
Seems like every presentation I do, somebody will ask me about black holes. It doesn't matter what the presentation's about. It's a very popular topic.
And well that they should, because in the end, they're going to be the only things remaining in the universe. All right. Yeah. Anyway. I'm not going to steal the thunder from my book. You're going to have to buy the book for all the pithy anecdotes.
Great. Well, thanks so much for coming, you all, and we'll see you next month.
Thank you, Stan. Thank you,
Thank
Hillary.
you.
This has been very
You're
enjoyable.
welcome.
Take care.
You.
Yay.
I'll end it unless, Karen, are you staying on because you have a question?
I have a question for you, but it's not at all about our topic today. So,
Well, hey, people can ask me about black holes anytime they want. Go for it.
I'm a clever guy. I could probably answer most
And
questions.
if he
that you
can't,
can
he
come
won't
up with.
lie. We already know that. So,
well, it actually has absolutely nothing to do with astronomy or the sun or anything else. Because I
Whoa.
think you and I worked together previously.
you and me?
Yes.
Oh,
'Cause did you work with the Psy Girls?
yes,
stuff?
absolutely.
Then you and I did work together because I did that at Apple Valley High School here in Minnesota.
Oh, wonderful. Yes, I know.
Yeah.
And I actually
I did
visited.
that
So,
first year where you and others came in and observed and talked about stuff and talked with students and everything. And I'm not at that school anymore.